So today's lesson is going to be on polarity of molecules in terms of the overall molecule and of the bonds. Now the bonds are going to, in a covalent compound, they are going to form based on the electronegativity. Because if you will remember, electronegativity is how well electrons are shared, and shared electrons do form covalent bonds. So we can look at bonds and we can base the bond and determine if it is polar or nonpolar simply on the values of these electronegativities that we can get. And we can actually use a chart for this. And now this chart I have posted on our website. All right, and these electronegativity values are on this chart here. All right, and they have been figured out by somebody much smarter than me who put it into a chart for us. All right, now depending on what textbook you read depends on the values. We're going to go with the values that you need to know for your exam in May based upon what your standard course of study says that you need to know. So a 0 to 0.3 is going to be a nonpolar bond. A 0.3 to 0.7 is going to be a polar bond. And anything over 1.7 we say is going to be an ionic bond. Now there's some leeway of interpretation with this. Different textbooks use slightly different values here for that. Okay, so these are not set in stone hard fast rules, but they are what we are going to use because this is what your test in May uses. All right, so what we can do is, let's say that we wanted to look at, let's use our Vesper theory practice worksheet that we've done and we've already gone over, okay? And let's look at number 2, carbon tetrachloride. So we have C for carbon and Cl, chlorine. So we're going to do CCl4, and we've already drawn it. Okay. So here's what we drew, and we do have our lone pairs on the outside of this. All right, so let's look at the bond itself. So in order to do this, we're just going to do a subtraction. All right, and it's always going to be the higher number minus the lower number to give us a positive value. So chlorine has a value of 3, and carbon has a value of 2.5. So if I was to subtract 3 minus 2.5, that gives me a value of 0.5. So we would say that this bond between the carbon and the chlorine is a polar bond. And the way we're going to draw this, we're always going to draw the arrow toward the more electronegative side with a positive here. All right, so this is how we would draw a polar bond, the arrow going towards the chlorine because chlorine is more electronegative. Now remember, a nonpolar bond is when electrons are shared equally. A polar bond is when electrons are not shared equally. An ionic bond is when we have a complete transfer of electrons. Okay, so when I have a polar bond, we are not sharing equally. Essentially what is happening here is chlorine is more electronegative than carbon. So chlorine is going to hog these electrons more than carbon. So chlorine gets the electrons. Every once in a while, carbon gets a shot at having those electrons. But for the bigger part, chlorine, is going to have the electrons. So if chlorine has the electrons most often, electrons are negative. So chlorine has what we call a partial negative charge. And carbon does not have the electrons as often. So when we lose electrons in an ionic bond, we become positive. So because carbon is not having those electrons as often, it is what we call a partial positive charge. All right? And it is a partial charge because chlorine does get the electrons sometimes. And it is a partial negative on the chlorine because chlorine does get the electrons sometimes. So carbon gets them sometimes. Chlorine gives them away. They do share, so these are partial charges. This is what we call a dipole. All right, so what this arrow shows the dipole of carbon tetrachloride, and it always goes towards the more negative the more electronegative element. Now, the way I think about it is carbon has a partial positive. So when I draw my arrow with this line here, what does that show? That sign is a positive. And when I go towards my chlorine, this right here is a negative. All right, so chlorine is partially negative, so there is the negative portion of it. Now, the bond between carbon and chlorine is polar. So how many polar bonds do I have? I have 1, 2, 3, 4 bonds between carbon and chlorine. So all 4 bonds are polar. The overall molecule itself is nonpolar. Ooh, so it is possible to have polar bonds, but a molecule itself that is nonpolar. Why is that? These chlorines are, the dipoles cancel out. So essentially, each one of these bonds has a dipole, okay? And the bonds are going to cancel each other out. So the chlorines in the up and down position, the way I've drawn it, those chlorines are canceling each other out. They are pulling equally in the same opposite direction. And then the chlorines from on the left and right are also pulling equally in opposite directions. So because we have an equal pull overall, we have a molecule that is overall non-polar. And if we were to look at a actual 3D model, so I've got a 3D model here. All right, and this is going to represent carbon tetrachloride. So here's the carbon in the center. And then I have the 4 tetrachlorides. So basically what we have is we have an equal pulling in all directions. So all 4 of these chlorines are pulling in opposite directions, okay? Pulling in opposite directions equally. So overall they cancel each other out to make the molecule non-polar. So let's just look at a couple of rules to help us determine is the molecule polar, is the overall molecule polar or nonpolar. The bonds, you'll have to look at these values. All right, but the molecule, we can determine if it's polar or nonpolar. All right, if there is a central atom, if all surrounding atoms are the same, we say it is nonpolar. For example, carbon dioxide. Looking at the central atom, and that's the key. Central atom, it is surrounded by an oxygen and an oxygen. Oxygen is oxygen. they are the same. So in this case, it is a nonpolar. If surrounding atoms are not the same, we say it is a polar. The bond itself is polar. Or not the bond itself, I'm sorry, the molecule itself is polar. For example, HCN, cyanic acid. When we look at this, carbon is the central atom. It is surrounded by hydrogen and nitrogen. Hydrogen is not nitrogen. Therefore, this carbon is surrounded by two different atoms, and therefore we say this molecule is polar. The dipole, the pull of the nitrogen, is going to be greater than the pull of the hydrogen. The electronegativity is what we're talking about, is going to be greater. So in this case, we've got more of a pull from the nitrogen. Overall, it is going to be polar. All right. One more thing. Trigonal pyramidal, bent, seesaw, T-shaped, and square pyramidal, these shapes will always be polar. Okay, so the pull is unequal on these shapes. If you are told lone pairs, in some classes we teach, like a lower level chemistry, we teach that lone pairs make something polar. That is a lie. I don't ever want to hear that. Never tell me that lone pairs make something polar. For example, let's look at something like this molecule, all right, right here, where I have a shape that is linear in the expanded octet form. I have two bonding pairs and 1, 2, 3, 4 lone pairs. So this shape, these lone pairs are pulling in equal and opposite directions. These two lone pairs are pulling equally opposite directions. These two lone pairs are pulling in equal and opposite directions. And my two outer elements are pulling in equal and opposite directions. So this is an example of something that has lone pairs but is nonpolar. So do not, please do not tell me that lone pairs make something polar. That is a lie. If there is no central atom, then we look at symmetry. If it is symmetrical, like oxygen, then it is nonpolar. Now notice there is no central atom here. That is the key. No central atom. If it is asymmetrical, it is a polar molecule. So to recap, we can look at polarity in one of two ways. We can look at it in terms of the bond, and we can look at it in terms of the entire molecule, the entire compound, okay? So the molecule itself, like I have in this example.